All right, new probability distribution today. We're going to look at what's called a binomial random variable and probability distribution. And in the third video of this set, we'll look at what's called a geometric random variable. So we'll be looking at what makes something a binomial, how to compute the probabilities for binomial distributions, as well as how to examine for mean, standard deviation, and actually make a connection to our normal distribution things also. So here we go. First we define what a binomial is. When the same chance process is repeated several times, we're often interested in what does or doesn't happen. Two possible outcomes. We're looking at successes versus failures. And if each trial is independent, we call this a binomial setting. And each success does have to have an equal chance of occurring as we go also. The four conditions to be a binomial setting are: is it binary? Are there two possible outcomes? Success versus failure. The probabilities of those, obviously, I hope you can see, would add up to 100%. Are the trials independent? If they're not independent, it can't be binomial. The number of trials, we must have a fixed number of trials that we're going to do. We're going to flip a coin 10 times. We're going to sample 100 people. We have to have a fixed number of trials. And finally, success. The probability of success must remain constant from trial to trial. So what we can do is we can remember that this has to satisfy the bins. We need to check bins whenever we're examining whether or not we can use a binomial probability distribution. So if we look at tossing a coin, we either get heads, we get tails. Those are two possible outcomes. It's binary. And if we define getting heads as being our success, the probability of heads, the probability of success is 0.5. The number of heads is a binomial random variable if we specify how many times we're going to flip the coin. The probability is always 1/2. Flipping a coin from one flip to another is independent. We have satisfied our bins. So the possible values for x are going to be whole numbers. They're our random variable. Except we're only going to have two: success versus failure. N and P. N is the number of trials. That's one parameter that defines our binomial distribution. And P is the probability of a success. When we look at a problem, you have to remember that not everything is capable of being assigned a binomial distribution. You have to check the bins: binary, independent, number, and success before you can determine if something is going to be a binomial distribution. And if it is, that's nice, because there's certain ways that we can approach these problems and certain nice things happen. So to introduce this probability, we're going to look at passing on genetic information. We're going to look at the probability that a family has children with type O blood. It's been found that 25% of children will have this type of blood. So the probability of success is 0.25. Geneticists say that the children receive genes from both parents independently. So these trials are going to be independent. Each kid, their blood type is independent of the others. If the parents have 5 children, okay, so there's our number. We have a fixed number. And the probability remains constant from trial to trial, 0.25, 0.25 to 0.25. We want to know what's the probability that we have 2 kids with type O blood. So that would be success, success, failure, failure, failure. We multiply these 5 probabilities. 0.25 times 0.25, and then 3 failures, so 0.75, and we can write that using exponents to get a probability of 0.02637. But there's other arrangements in which 2 out of 5 children can have type O blood. When we write this, we're saying the first kid does, the second kid does, and the third, fourth, and fifth kid does not. But they don't have to come in that order. It could be any of these others. And in each one of these arrangements, you should be able to verify that we have the same probability for each of them. And that's because no matter where we are, we're multiplying 0.25 twice and 0.75 3 times. So it's this right here. It just changes the order. And with multiplication, we can multiply in whatever order we want. So the probability that x equals 2, the probability that 2 children of 5 have type O blood is going to be 10 times 0.25 squared times 0.75 cubed, giving us a total probability of 0.2637. Okay, so let's generalize. K successes and N trials. So the probability that x equals K means probability exactly K successes and N trials. So we take the number of arrangements in the previous problem, that was 10, times the probability of success times how many successes times the probability of failure raised to how many failures we're going to have. And we don't need to count by hand all the number of arrangements. We can use our binomial coefficient. We see this with our binomial expansion. We see this with Pascal's triangle. It's our combinations operator. N choose K. N factorial over K factorial, N minus K factorial. Okay, so let's dive in and use this formula. Let's generalize the formula in all its glory first, I suppose. So instead of saying number of arrangements, we can call it N choose K times P to the K times 1 minus P to the N minus K. Wow, what does that mean? Well, let's look. Number of arrangements, probability of success times multiplied the number of successes that we want, and then probability of N minus K failures. So 2 successes means 3 failures. So 2 and 3. These exponents will always add up to however many trials we have in our problem. So let's use it. Find the probability that exactly 3 children have type O. Give this a try. See if you can't use our formula and answer this question. Pause the video and do the calculation right now. So we know we're binomial. N is 5, P is 0.25. So the probability that x equals 3 will be 5 choose 3 times 0.25 cubed times 0.75 squared for the probability of approximately 8.8%. Second question. Should the parents be surprised if more than 3 of their children have type O blood? Well, we have to interpret this. To answer, we need to find the probability that x is greater than or equal to 3, 3 or more, or greater than 3. It says more than 3. So we interpret it to this probability notation, and that means the probability of x equaling 3 or x equaling 5. I'm having difficulty talking, my apologies. X equals 4 or x equals 5. We do 2 binomial calculations. We crank the numbers, we get 0.01563 as the probability. So I would say yes, since there's only a 1.5% chance that more than 3 out of 5 have type O blood, the parent should be surprised. So this is where we shall stop for today after our basic calculations. Remember, you need to deal with bins every time you approach these problems. Is a binomial distribution necessary and applicable in each problem you attempt?